I'm Oleg Anastasyev. I'm a lead platform developer at OK.ru. And what is OK.ru? We have 45 million audience and 80 million monthly audience. We are top 4 social networking site. According to Comscore data, OK.ru is top 7 of all websites on total time spent of our users online. And OK.ru is fairly high loaded. We have about a lot of requests to our front ends every second. This load is processed by 8,000 servers located in 5 data centers. All these data centers are located in Moscow, and network latency is small between them. This, of course, simplifies our multi-data center setups. We use Cassandra since 2010. We started from version 0.6 and did a lot of development of our own branch. We have few 1.2 version clusters, and this year we also started to have a Cassandra 2 in production. This is a quick list of patches I submitted to mainline Cassandra 2 codebase during the testing. This year we expanded our deployments of Cassandra. You can see the current deployment numbers here. More data and more clusters are managed by Cassandra now. Our fastest cluster is doing 1.5 million operations per second. Our largest one now stores more than 100 terabytes. But these clusters are more like usual NoSQL deployments. This year, we are aimed to implement a storage system able to replace our main consistent data storage, the Microsoft SQL Server. It is used in OK.ru since we started. It manages data with ACT requirements. These data, also known as business entities, like users, money, and so on. They are typically read-most and modified by several concurrent processes. Until this year, we have a little more than 200 SQL servers in production. A simple sharding scheme is used to partition data across several servers. A hash function is applied to an ID of an entity, resulting in some token. This token then mapped to nodes which this token instance resides. To implement master detail relationships, we are making sure token of the master entity is equal to token of detail entity ID. So this way, both master and detail records are forced to reside on the same node. This way, we form a local transaction group of tables. This allows us not to use two-phase commit for data to remain consistent. The local node transaction is enough in most cases. We cannot use two-phase commit due to its performance, but this is not the only feature we don't use to make the SQL server faster. Database side joins. Instead, we use either denormalization or performing joins on the application server side. Foreign key constraint because we partition data across several nodes. Stored procedures and triggers also add to CPU load of the database server, so we don't use them. To reduce lock contention, we use read and commit at isolation level when out of transaction. Also, to reduce lock contention, we try to make transaction as short-lived as possible. And because of this, we are not making any massive updates or deletes. And of course, when it comes to queries on the database tables, we are making sure all queries are being performed using pre-built indexes. This allows us to squeeze almost all performance from SQL servers, but this cannot solve a usual SQL shortcomings. SQL Server has no automatic scale-out, so we do this manually with downtime for a part of the data. And many other database maintenance tasks require downtime. SQL write performance often becomes unsatisfactory for us. This forces us to scale out, and this again is manual and comes with downtime. We regularly see blue screen of deaths when server reaches some load level, and it's very hard to trace with no access to its source code. So it's much like trying to find a magic spell. And this runs on expensive hardware. High availability cluster setup is 10 times the price of the commodity server. Still, when it comes to failover, it is very fragile. Often standby node fail in several minutes after a failover attempt. And this expensive setup cannot serve its data on data center partition. And this limits our site unavailability. Let's look more closely at the data causing so many troubles. This is how the transaction adding photo into an album could possibly look like. Here we start a new transaction on the partition of album, lock it to prevent concurrent modification, create a photo in photos table, and if photo status allows, increment visible photo counter of album, updating data in album table. This is a fairly simple transaction commonly seen in SQL world. Let's examine some of its properties. It reads some data, applies some logic to it, and saves it back to storage. Typically, as several records from different tables participate in a single transaction, so they must be modified atomically. Typically, same data can be modified by several independent processes. If one tries to re-implement all of these to NoSQL solution, he or she would face the following usual NoSQL problems. The learning curve is one thing to consider. Switching mindset from ACID to distributed programming is hard. We learned that product development on NoSQL engines is too sophisticated. It often requires full remodel of data schema and massive code changes due to changing requirements. Some features are just too hard to implement in NoSQL. Often, NoSQL projects miss their deadline. Product developers need to address problems of data storage in application-specific way. Developing code around atomicity of update to several entities, conflict resolutions, and so on. As a result, many systems, to our experience, include ad hoc, fragile, and buggy ACID implementation. All of this means that product development time to market slows down, and this is pain. So we need a new storage with reasonable balance between consistency, availability, and performance. It should be fast and easy to learn, so product developers can focus on product, not on data. So it should provide ACID transactions with rollback possibility, and it should mimic SQL. For operations, it should be able to read from and modify data in case of data center failure or partition. We don't support operation in the partitioned data center. We just switch external traffic to other healthy data centers. It should have automatic scale out, and of course, it should run on commodity hardware. And we wanted new solution to be open source, so we can fix it if necessary. So where to start? We could take some SQL engine and develop a lot there, including kind of distributed SQL. Or we can take some recent NoSQL storage and develop ACID and SQL by ourselves. Implementing full SQL seems like very sophisticated effort, but we use very limited subset of SQL. If you remember, this set looks very much like Cassandra's SQL. This is good news. Let's look what else could we take off the shelf with Cassandra. Well, scale out and best of the class write performance. Quorums work for durability in ACID, and speculative retry makes slow nodes not to affect latency. We had to alter retry so it works more flawlessly. You can look into the ticket for details. And logit batches, this ensures changes are atomically applied to storage. This works for the A in ACID. Well, lightweight transaction for consistency and isolation. Let's look at what our simple SQL transaction does. Read, modify, write. Because lightweight transaction is some kind of optimistic locking, it could be used to implement this scenario. It could help us to resolve concurrent modifications to same KL as well. Could we use it to consistently modify a few records from different partitions, making changes to several tables in a single batch? No. It is restricted to single partition of a single table. And lightweight transaction requires 4 round trips to complete, which is slow. And this speed is not acceptable for us. So lightweight transactions are useless for us. What makes SQL development easy? Ability not to model data for read patterns upfront. We want just to build a new index for new query. So maybe secondary indexes could fit for this purpose. In short, no. So we took the best from Cassandra and implemented our own storage, which we called C1. So the main features of C1 are AC transactions resistant to failures on many tables and rows with ability to roll back. First-class index allows SQLs consistent, scalable, and fast with no additional coding to support new indexes. And ability to build index on existing data. So let's have a look at how it works. When we built our system, we broke it down into 3 main components. One is storage nodes. These nodes form Cassandra ring and are used for storing and retrieving data. These are like any Cassandra nodes out there in the wild. Second is update coordinator nodes. They are responsible for transaction management. And the third part is client nodes. All components have different responsibilities, but they are all part of the same cluster. They use Cassandra native messaging protocol for communication and use gossip. To decide which nodes are up and down, to replicate data schema, I mean tables, columns, indexes, and so on, to the memory of all machines. To exchange the partitioning and cluster topology information. Additionally, it exchanges information about presence and configuration of Cassandra 1 update service nodes. Let's go deeper. Clients. They are not exactly clients, but application servers. They all implemented in Java language, and we have a lot of them. They don't use any driver. They use FAT client mode to join directly to the Cassandra ring. This allows us to send data requests directly to the nodes containing data. So request coordination, I mean communication with correct replicas, conflict resolution, and so on, is performed by the client itself. This is faster. We eliminated a network round trip to coordination node and saved some CPU ticks. But what is more important, this makes a system more reliable, avoiding one possible point of failure, a coordinator node. And now we have a full freedom to what node to communicate. And we communicate directly to storage nodes reading data outside of transaction. But when a transaction is opened, this would not work. This is the moment then update service nodes must participate, so we direct the read and write requests in transaction scope to them. Let's take a look what exactly update services do. They manage locks on row keys. Pessimistic locking is the simplest way to implement isolation in ACID. It generates monotonically increased microsecond timestamps. So a previous transaction on the same cell will have timestamp less than timestamp of subsequent one. This makes Cassandra conflict resolution work properly. Timestamps which are issued by clients typically suffer from local clock drift problem. This makes a C1 timestamps a Lampard timestamp. Update services also manage state of active transaction, perform commits and rollbacks. And they also implement their own failure detection and failover. Our data and transaction are already naturally sharded to local transaction groups. So we decided to partition all transactions to groups here. So for every token, at every moment, there is a single transaction group master responsible for the transactions for these keys. This way, we achieved locking to be a simple in-memory locking. Well, this concept is not new. It can be found in HBase, for example, but there are some interesting details on how failures are detected and managed. We placed 2 nodes to every data center. These nodes have their own heartbeat protocol. Every update service node sends to every other update service node its current local view of the cluster state. In a local view, node decides, are other nodes down or up? On a reception on these local views, every node combines all messages together and decides on the quorum cluster state. Node is decided up if majority of nodes say so. Node is considered down if majority says it is down. The same applies for deciding node itself. So if majority says it is not reachable, node decides it's down itself. Because we want failed node to be detected as fast as possible, we made heartbeat to happen every 50 milliseconds. This is small latency for Java program, so we use the garbage first collector here so we can keep GC pauses low. This way, we achieved only a 200 milliseconds pass from actual failure to its detection. But it is not enough to just detect a failure is happening now. It has to be managed right. So let's talk about how transaction failure for transaction group 50 could be managed. We defined a master replacement strategy. I mean, which nodes will be possible substitutes for a master node on its failure. We wanted to survive data center failures, so we defined that first substitute is a node from the second data center and second substitute from the third. This strategy is selected once for current topology and never changed on runtime. Then master election protocol is simple. Master is never elected. It is being determined by the order of live nodes. If primary node is live, it is the active master now. If it is not, then the first substitute becomes the active master, and so on. But how could clients know which of these three nodes is active master at the moment, to which they could direct their transactions? 50 milliseconds tick is too fast to send to 800 nodes. This is a problem. Clients could direct their transaction request to failed node and get a lot of timeouts. Clients don't need to know about it at all. They direct their transaction requests to all three. The trick is that only currently active update service node will respond. Others will stay silent. So the client continues its transaction with first responded update service. But what happens to unresponded transaction start requests on substitute nodes? They are placed to unborn transaction queue. On failover, a new master will replay these requests, try to open all transactions, and send a response to clients. If failover did not happen within transaction timeout, they are just thrown away from substitute's memory. Now, let's take a look what else update services have in their memory. This is not much. It has a memory logs table for the currently held logs and transaction state mem table. When client sends us new transaction on a some key, it places a log to the logs table and reads of current raw state from Cassandra storage nodes. Then it caches it to the state mem table and returns it back to client as a consistent state of a row. Then client decides on changes and requests to modify some record. Update service applies a new state to its mem table. Please note that there is no any write happening to Cassandra storage nodes at this point. On a subsequent read query in the same transaction, it may query data from storage if necessary, and from the state mem table. Then it merges data into the final result and returns it back to client. This way, client reads its own uncommitted mutations. On commit, Cassandra logged batch is created from current transaction state and sent to Cassandra storage. then Cassandra applies it atomically, so update services release all logs, and transaction is committed at this point. Then how a rollback could be implemented? Anybody knows? Any ideas? All state just clear it from memory, and that's it. So we implemented ACID. We use logit batches for atomicity. We make consistency checks at application. We can roll back if necessary. We provide isolation by means of logs, and we have read committed isolation level. And Cassandra is responsible for durability. Now let's talk about indexes. Let's look at the real-world problem. Here we have some table with its ID of the owner, and a modified date. And we want to select data from this photos table by owner, which were modified last day. How could we solve this problem in Cassandra? Could we create a secondary index on owner and modified columns? Anybody tried? No. Secondary indices do not support indexes on composite case. And as Jonathan mentioned it in keynote today, they are good fit for high cardinality expressions. And all nodes are queried for them, so they don't scale. And a limit of 100,000 deletions per index makes them unusable in OLTP system. So to overcome this restriction of local index design, we implemented first-class indexes by ourselves and named them global indexes. Suppose we have a table with photos. This is the photo ID column, and it is the primary key. Using the create global index statement, we make C1 to create another table in Cassandra, a copy of original table, but ordered by indexing expression. Then select statement on index expression is simply translated into select on an index table with the same where clause. And this kind of queries Cassandra executes fast. And it scales well. We hack it on SQL engine, so this translation is performed automatically. The index build is performed online and allows normal operations. The build process to create a consistent index is sophisticated, and it's a very interesting topic by itself. I'll not cover it now. Maybe you can ask me after the presentation if you are interested. Instead, let's look how a write to index a table works on update server. Then client requests to modify a record in a table with index. And this information was received earlier from data schema. Update service, in addition to mutation of the original table, generates mutations for an index as well. It uses the original state of a row located in transaction and current modified state to figure out the necessary changes to index. So consistent copy of data to global index table is performed automatically. And no additional reads or logs are performed to maintain consistent index here. Now, thanks to ACID, we have global indexes. And now we can just create an index for a new query in response to the new business requirements. Comparing to SQL Server, it has very little write speed penalty. Just one write to a mem table. At the present time, this system is working in our production for more than half of the year. We migrated several systems to it. The most interesting is photo system. It stores not binary media, but business information about the photos. Photos are shared much on the social network, so we have a lot of them, and they are read most. The old system used for them had a replication factor 1 and did not provide any tolerance on data center failure. The old system used 58 server nodes, and their load was 100%. The new system has replication factor 3. Every data center have their own copy of the data. A total of 69 nodes are used for this system, but their price is much lower. And it has the 3 times capacity of the old system. We lowered our rate on photos much from thousands to just tens per day. And it is fast. You can see the latency numbers on the slide. So it works well at the moment. So we are migrating more and more of SQL data to this system. We experienced 2 real data center failures with this system at the moment. First was flawless. Second was not so flawless because of bug in, surprise, Cassandra messaging. While we were implementing this, we found and fixed it a lot to mainline Cassandra as well. I listed the most interesting, not merged yet tickets here. They all made for Cassandra 2, so you can make use of compressed commit logs, for example. Jonathan told about on today's keynotes planned for free version of Cassandra. The most interesting here is what I call Night of the Living Dead. Due to current bugs in Cassandra, there is a chance that records removed far in past are resurrected after a node restart. This surprisingly happened at night. So we had a 15 terabyte data set, useless because of this. Luckily, we had a backup of that data so on the secondary storage, so we took data from there. So that's all I wanted to tell you today. Thank you. Questions?
Yeah.
Yep.
About global index.
Yep.
How do you handle wide partition, very wide partition?
Very wide partition, I see. Very wide partitions are not handled well by Cassandra itself, actually, because a lot of tombstones in it. Yep. This is the flaw of the original Cassandra. So we try make them not so wide. This is the only recipe at the moment.
So in your example, you put the timestamps as you put an index on your timestamp, right?
I understood the question. We have a special field actually in that exact table which name it timestamp partition. Yes, and value of this partition is changing every 5 minutes or every minute.
So you are bucketing.
Yep, exactly. Yeah. Any other questions?
There are a lot of places for split brains problems in your architecture.
Not much, actually, because as I told, is active master currently live or not is decided by the quorum of nodes. So if the update service does not see quorum of nodes, he supposes he's dead. So if quorum decides he's alive, then only then he's alive. So split brain is not possible here because there will be no quorum on partition.
So it means that transaction cannot be highly available in case of partition.
In the partitioned data center, yes, this is. But we chosen not to support operations in the partitioned data center. We switch the external traffic from clients to the healthy data centers. So if the partitioned data center doesn't work, it does not matter. Masters, update service masters will switch over because they don't see, in partitioned data center, each of the masters don't see the quorum, so they are dead. And so they switch to the healthy.
In special cases where you have very weird partition, two masters?
If in the very, very weird condition when each of them sees quorum,
Yes.
but this is actually we tried to imagine this how could it be in numbers, and we cannot try to imagine it.
Because it happened to Elasticsearch that in some
To?
cases, Elasticsearch,
Mhm.
there is a split brain partition where there is two masters elected and two masters are receiving write.
Yes, the
They went to the
split partition problem. I know the split brain problem, but not in this design. Because quorum, again, the heartbeat protocol is quorum based. So if you have very, very, very partition, but I actually cannot imagine how it could be. Maybe yes, but I think it's kind of non-realistic.
So is this open source so we could get Jepson and try and recreate that scenario?
No, it's not open source. Sorry.
So what was the actual transaction protocol you used? I mean, algorithm you used? So it's like an MPCC algorithm or?
This is plain AC transaction. You open transaction, you write to it, you commit it.
Yeah, but the actual distributed transaction algorithm.
This is not distributed. It is handled by, it is partitioned. The downside of this is that distributed transactions, I mean transaction on the keys from different tokens of different tokens is not possible in this system.
So the transaction is local to a single key?
The transaction goes on the keys of the same token.
Okay, so the transaction is local
If-
to a partition. Then.
If some user has some ID, he writes a lot of records, other detail records created for this user. This is master detail record. We make sure that the token of detail records is the same as the token of the master records. So if you do some transaction to change user's data, this transaction happens on the keys of the same token.
Okay, so the transaction is local to a partition then, right?
The transaction is local to keys of the same token. Yes, to partition of the update service. Yes.
But the data is actually replicated, right? You use duplication.
Data replicated by Cassandra storage nodes. Yes.
Okay, so
But after commit. When we
so if you have replicated data, you have essentially a replicated transaction. It's a distributed transaction.
not exactly. The transaction itself happens in the memory of the update service. Then, when we commit, the logit batch is created, and this logit batch is being written to Cassandra storage cluster. The Cassandra storage cluster handles the replication. After we have an acknowledge from the Cassandra storage cluster for the quorum, actually, of Cassandra storage nodes. At this point, we decide that transaction is actually persisted.
Okay, so you perform the transactions within the transaction coordinator, and then you replicate those transactions to the actual storage.
Yep. Storage does a replication. Yes.
Well, I mean, that arrow where it says free, right? You actually replicate that transaction log onto the storage, right?
Yep.
So that means that replication is serial, right? The question.
That replication?
Yeah, that replication, that arrow number 3 there.
Yep. That's a replication on the quorum. Yes.
Okay.
It can be.
Is they synchronous or synchronous?
Quorum. So we send to 3 and get results from 2.
No, with the client will perform a transaction.
Yes. Yes. It waits for the logit batch write to complete.
Right. So it waits for that number 3 arrow to complete, basically, right?
Yep. Exactly. We have to end now. If you have any questions, I will be right outside of this